Carbide burrs are versatile rotary tools essential for precision work in metalworking, and their effectiveness largely hinges on the cut type, double cut or single cut, which determines how they interact with different materials. In this detailed exploration, we'll compare the intersecting flutes of double cut burrs, ideal for achieving finer finishes on hard metals like steel, prevalent in Ohio's aerospace industry, against the parallel flutes of single cut burrs, which provide cooler, coarser removal on softer metals like aluminum. We'll verbally explain practical scenarios, such as using single-cut burrs to prevent clogging when deburring brass fittings, and include tips on RPM settings and heat management. To illustrate key concepts, I'll describe static before and after sketches that could be used in educational materials or videos, focusing on visual clarity without animation. Understanding flute designs and their impact. The flutes on a carbide burr are the helical grooves that form the cutting edges, playing a crucial role in chip formation, removal, and overall tool performance. Double-cut burrs feature two sets of intersecting flutes, creating a crisscross pattern that resembles a grid of sharp, diamond-like points. This design breaks down material into smaller, finer chips, resulting in smoother finishes and reduced vibration during operation. It's particularly suited for hard metals like steel, where the intersecting flutes provide more cutting edges per rotation, allowing for controlled, precise material removal without excessive force. In Ohio's aerospace sector, think of facilities near Mason, such as those in Cincinnati supporting companies like GE Aviation. Double-cut burrs are commonly used to refine steel components in turbine parts or airframe assemblies. The finer chip size minimizes surface roughness, achieving a polished look that's critical for parts requiring tight tolerances and aerodynamic efficiency. However, this aggressive cutting can generate more heat if not managed properly, as the multiple edges create friction on dense materials. In contrast, single-cut burrs have a single set of parallel flutes spiraling in one direction, forming broader, straighter channels that produce larger chips and a coarser finish. This setup promotes cooler operation because the wider flutes allow for better airflow and easier chip ejection, reducing heat buildup and the risk of workpiece distortion. Single-cut burrs excel on softer metals like aluminum, where their design facilitates rapid, efficient removal without the tool binding or overheating. For instance, in aluminum fabrication, common in Ohio's automotive and light manufacturing scenes, the parallel flutes shear off bigger chunks cleanly, leaving a rougher but functional surface that's often sufficient for initial shaping before finer finishing. The key advantage here is the cooler cut, as the simpler flute structure dissipates heat more effectively, making it less likely to soften or warp sensitive materials. To visualize this comparison, imagine a static before and after sketch. On the left, before, a cross-section of a double-cut burr head shows intersecting lines forming a web of small, sharp intersections, labeled finer chips for smooth steel finishes. On the right, after, the same view for a single-cut burr displays straight, parallel grooves, labeled larger chips for cool aluminum removal. Below each, a magnified material sample illustrates the outcome: a silky, refined steel surface from the double cut versus a textured, grooved aluminum surface from the single cut, highlighting the finish differences with arrows pointing to chip sizes. Verbal explanations of practical scenarios. Let's walk through some everyday scenarios verbally to bring these differences to life, emphasizing how the flute designs influence real-world use. Picture a mechanic in a Mason, Ohio garage working on aerospace-inspired custom parts, perhaps prototyping steel brackets for a drone frame. Using a double-cut cylindrical burr on hardened steel, the intersecting flutes grind away burrs from machined edges, producing tiny chips that scatter easily and leave a mirror-like finish. The narration might go, "As the burr spins, its crisscross flutes slice into the steel like a fine rasp, breaking down the metal into dust-like particles that don't clog the tool, ensuring the part meets the precise specs needed for Ohio's high-tech aerospace demands, smooth enough to reduce drag and prevent stress fractures." Now contrast that with a single-cut scenario, such as deburring brass fittings for plumbing or electrical work in a home workshop. Brass, being a softer alloy, can gum up tools if chips aren't ejected properly. But a single-cut ball burr avoids this by generating larger curls of material that peel away without sticking. Verbally, you're fitting brass connectors for a custom lamp project, and the single-cut's parallel flutes carve out the excess with broad strokes, creating ribbon-like chips that fly off effortlessly, preventing the clogging that could happen with a double cut on this malleable metal. It's like shaving wood with a plane, keeping things cool and clean without the tool binding mid-task. This approach is ideal for softer, non-ferrous metals, where the coarser removal speeds up the process without sacrificing control. Another scenario, in an aluminum bike frame repair, relevant to Ohio's cycling community around trails in nearby Cincinnati, a single-cut flame burr roughs out weld beads coarsely but coolly, avoiding the melting point issues that heat from a double cut might cause. The verbal explanation: the parallel flutes channel away big aluminum shavings, keeping the tool and workpiece from overheating, resulting in a quick deburr that leaves intentional texture for better paint adhesion later. For a before and after sketch here, the before side depicts a jagged, burred brass fitting with labels like rough edges causing clogs, while the after shows a smooth, deburred version post-single cut, with arrows illustrating large chip ejection and a note on no clogging, cooler operation. Tips on RPM settings and heat management: optimizing RPM, revolutions per minute, and managing heat are vital for safe, effective burr use, as improper settings can lead to tool wear, workpiece damage, or injury. For double-cut burrs on hard metals like steel, start with moderate RPMs around 15,000 to 25,000 to leverage the intersecting flute's precision without excessive friction. Too high, over 30,000, can cause overheating, while too low reduces efficiency. On softer aluminum with single-cut burrs, higher RPMs of 20,000 to 35,000 work best, as the parallel flutes benefit from speed to fling away larger chips and maintain coolness. Heat management tips include using light, intermittent pressure to let flutes do the work, apply in short bursts to allow cooling, and incorporate air blast or lubricants, like cutting oil for steel, to dissipate heat. For aluminum, avoid lubricants to prevent chip adhesion, relying instead on the flute design for natural cooling. Always wear PPE and work in well-ventilated areas, especially in Ohio's variable winter humidity that can affect metal behavior. Illustrating this with a static sketch, a split panel diagram shows before as an overheated burr with smoke and warped metal, labeled high RPM without brakes, versus after as a clean, cool operation with airflow arrows, noting optimal 20,000 RPM with pauses for heat control.